everyone, in today's video we are going to continue talking about normal distributions. We're going to extend that conversation today to talk about standard normal distributions and also z-scores. So in this video you're going to learn to label the normally distributed curve when it's standard using mean and standard deviation still. Then we are going to use a calculator, specifically Zscores, to find percentages and probabilities when we're given a problem that's not covered by the empirical rule. And we're also going to use Zscores to find x values of a normal distribution when we're told the area or the percentage underneath the curve. And then last, we're also going to calculate z-scores to standardize data so that we can analyze and compare different situations. So let's get started. This first problem is the same context that we started with last time. We have a machine that fills a 12-ounce potato chip bag. It places chips in the bag. Not all bags weigh exactly 12 ounces. The weight of the chips is placed is normally distributed with a mean of 12.4 ounces and with a standard deviation of 0.2. So we are working with the same problem we were doing before, where our mean is 12.4, and then we are labeling our x-axis the same way that we did before. The conundrum that we're going to get into today is that the problems are not going to give us bounds that are right on these standard deviations. So let's look at an example of that. If you purchase a bag filled by this dispenser, what is the likelihood that it has less than 12.3 ounces? So remember, we know that our mean is 12.4, and if we go one standard deviation to the left, that's 12.2. 12.3 on our x-axis is in between the mean and that standard deviation. So we can't use empirical rule because at very best we'd be giving a kind of bad guess at it. So if we are looking for less than 12.3, I've got my line at 12.3. I'm going to shade everything smaller than, and we're going to use Zscores or a calculator to help us with this. So when we go over to Zscores, you are going to go into your keyboard, and underneath functions you'll see that there's this section that says dist, and that stands for distributions. So we have a lot of different kinds of distributions. The curriculum for Algebra 2, we're only going to use a couple of these buttons. The one that we are using today is called normal dist because we're doing a normal distribution curve. So I'm going to click that. I'm also going to click Find Cumulative Probability because that's the type of problem that we're doing. And you'll notice that there's this Zoom Fit button here. If I click that Zoom Fit button, it's going to zoom fit to my curve. So I'm going to back up a little bit. Notice here that it is giving me my mean and my standard deviation, but that's not true for this problem that I'm working on. So when I first create this normal distribution and get that initial piece, I need to tell it what the mean and the normal distribution are. So I'm first going to tell it the mean, since that's what it's listing here first. So I'm going to put 12.4. Then I'm going to put a comma, and I'm going to give the standard deviation. So now you see it says mean, comma, standard deviation, because I changed the mean. If we leave it as it is here, then it's going to operate with a mean of 0 and a standard deviation of 1. That's going to be fine for our standard distributions that we're going to get to later, but for right now, that's not the kind of problem we're doing because we have a different mean. So I'm going to put the mean, comma, and then the standard deviation, which is 0.2 in this one, in my parenthesis. And you'll notice now that this curve, if I click Find Cumulative CDF and click Zoom Fit, it's going to zoom in. Notice that my x-axis is exactly what I was drawing a moment ago. Now it's shaded under the entire curve. That's not what I want. I have a very specific situation that I'm dealing with here, the left side of the curve up to 12.3. So you'll see that it's asking you for the minimum and the maximum. The minimum is already listed as negative infinity, so I only need to change the maximum here by typing in 12.3. When I do that, it immediately shades the correct section of my graph, as we can see, and it calculates your likelihood here. So we have a 30% or 30.85%. Let's round to 2 decimal places. So let's see, our minimum was the far left, so that's negative infinity. The max was where our shading stopped, that's 12.3. And the percentage of the graph that's shaded there, based on what Desmos just told us, is 30.85%. Remember, to convert a decimal to a percentage, you move the decimal 2 places to the right to get that percentage. Okay, so now we're going to maintain the same area for this next problem, but it's going to ask us to build on our question. So if a factory produces 5,000 bags of potato chips in 1 hour, how many bags would you expect to weigh less than 12.3 ounces? So notice I'm being asked a quantity here. How many bags are we talking about? Not a percentage question. We are still working with the same region that's shading less than 12.3 ounces. So the way that we're going to calculate this is we're going to take that 5,000 bags and we're going to multiply by the decimal that Desmos gave us. We are not going to just multiply by 0.3085 because that's a rounded number. Instead, I'm going to go back into Desmos. I'm going to copy all of that number, and in my next line, I'm going to do 5,000 times, and then I'm going to hit Control V to paste that number in. So this is still a rounded number, but it is going to be more accurate than just using 2 or 4 decimal places. So I've used that entire number, and I know that my answer is 1,542.68. So since it's bags of potato chips, let's round to a whole number. 1,543 bags of potato chips are going to be less than 12.3 ounces. So again, in this spot here, I put the likelihood decimal unrounded because that gives us the most accurate answer. Okay, so let's try another situation. If you purchase a bag filled by this dispenser, what is the likelihood that it has more than 12.75 ounces? So let's think about where that shading would happen on our curve again. We still have 12.4 in the center, then 12.6 and 12.8, 2 standard deviations to the right. 12.75 on the x-axis is going to fall somewhere in between there. And we're looking at more than, so we're shading all the way to the right. That means that our minimum of our shaded area, the smallest x value, is that 12.75, and the maximum, because it goes all the way to the right, is positive infinity. So let's go over to Desmos, clear out the problem that we have, and start a new normal distribution where we have a mean of 12.4 and a standard deviation of 0.2. We are finding the cumulative probability, and then this minimum, we're going to put the 12.75 there. We're going to leave the maximum at infinity. If you accidentally click this, notice that it goes away immediately. If you just click back over into some other part of the problem, then it will come back. So if you accidentally type 12.75 there and then realize, oh no, I put it in the wrong one, just delete what you have and then click over into either your mean and standard deviation or your minimum, and that infinity sign will come back. So I've got my shaded region here, and I have, it looks like 4%. If I round to 2 decimal places, it's still going to be 4.01%. So pretty close to 4% there. Oh, did I click normal CDF? Did I mess up? Nope, I did. I clicked the find cumulative. Okay, so let's write that down. That's 4.01%. I'm going to be rounding pretty much everything to 2 decimal places today. Okay, the next one says if you purchase a bag filled by this dispenser, what's the likelihood that it's between 12 and 12.5? So in this one, our minimum is going to be 12, our maximum is going to be 12.5. On our curve, that's 0.2, so this one is 12 over here. So we're going from there, but we're going all the way up to 12.5, which is going to be off of a standard deviation. We're looking at that region. So let's put that one into Desmos. Because this is the same problem now, I'm going to just remove that minimum and make it 12. And this maximum, I'm going to change it to that 12.5. You don't need to completely restart the problem every time if your mean and standard deviation are still the same. All right, so here I have 66.87% for that shaded region. Okay, we have another one where we're looking at how many, and we're still working within that 12 and 12.5 bags, but this time we're looking at 7,000 bags of potato chips, and how many of those 7,000. So as we did before, we are going to copy this value from Desmos, and then we're going to put in the 7,000 times, and then I'm going to paste that, I'm going to use Control V to paste that very detailed number and get our number here. We're going to round to whole numbers because we're talking about bags of potato chips. So 4,681 bags. Okay, so now let's go ahead and move on to our next type of problem that we might have. There's a function called the inverse of a normal distribution. And just like we've studied inverses before, inverses are the kind of flipped version, right? We've talked about that a lot, flipping the x's and the y's and that kind of thing. In this situation, when we're looking at a normal distribution, but instead of being told the x-axis and asked to find the percentage, sometimes we're going to be told the percentage of the shaded region, and we're going to have to figure out what that x-axis value is. So these next two problems are going to do that. Let's look at the situation. The price of printers is normally distributed with a mean cost of $2.15. So I'm going to go ahead and put $2.15 as my mean on both of these. And a standard deviation of 35. So let's go ahead and label our standard deviations. We've got 250, 285, 320. That's on both. And then if we go to the left, we've got 180, then 145, and 110. Okay, so we have our curves labeled. So now let's look at the situations. How much would a printer that is more expensive than the cheapest 25% of printers cost? So we know that we're looking at 25%. We want to know where the number for the lowest 25% is, because then we'll know the minimum cost of the more expensive ones. Using the empirical rule, I know that this section is 2.5%, and if I add a little more, that's 13.5, so that's 16%. I'm still not there. But this section is 34%, so I'm only going to add in part of it because I'm trying to look for the shaded region that gives us 25%. So that's roughly an area of 25. And what we want to know is what that x value is. So we are again going to go to Desmos to get some help with this. This time, though, we are going to, in our functions, we're going to set up our normal distribution just like we did before. So we have a mean of $2.15 and a standard deviation of $35. We're not going to click the find cumulative probability, though. We're going to go down to the next line. If you want to zoom fit it so you can see your curve, you can. But this time, we're going to set up another function because we've told it what our original distribution is. We're going to choose the inverse CDF. And what this is going to do is allow us to make some use of the normal distribution. So in front of the normal distribution, I'm going to type D is equal to. And then when I do my inverse CDF, I'm going to identify the normal distribution that I just named D, put a comma, and then I'm going to tell it the percentage that I'm looking to find. So I'm looking for 25%, which is 0.25. Now, notice when we were shading here, we shaded from the left up to that 25% point. And that is always what the inverse CDF is going to do. It's going to start on the left and shade to the right. That's going to introduce a conundrum that we're going to have to be smart about in this next problem. So our normal distribution with our inverse CDF gives us 191.39 as the x value. If you are ever asked to show your work for a problem like this, I'm asking for that information that you put in the calculator so I can check your work. So I want to see D is equal to that normal distribution, and in parentheses we put 215, 35. That's part of showing your work. And then I also want to see the inverse CDF, what you put in. So you're writing inverse CDF, D, and then here is where that number that you put in as a decimal, 0.25 goes. And that is equal to what we just found, 191.39. And so that is my answer. That is the x value, what x is equal to. Okay, so let's look at another one that has a slightly different situation. How much does the cheapest of the top 30% of printers cost? So I know based off of empirical rule, I'm going to be, again, somewhere in between the mean and one standard deviation. This is saying how much is that x value for this top percent, this 30% that I know. Now, because the inverse CDF always starts on the left, I am not going to use a 0.3 for my percentage there. I'm going to look at what is this? What is the other part of the graph up to that line for that x value I'm trying to find? The entire graph is 100%. So 100 minus 30 is 70. So that means we're looking in Desmos at this 70%. So I'm going to set up my problem the same. If I show my work, I'm going to say D is equal to the normal distribution. And I'm about to do this all in Desmos. I've got the same mean and standard deviation here. When I do my inverse CDF, though, oops, for my percentage, I'm going to put the 0.7, or the 70%. That is going to tell me what the x value is for that spot that we're looking for. Okay, so let's put all of that in so we can see what we get. We have exactly the same problem as we just did, except for this is a 70%, so that's a 0.7 there, and that calculated very quickly for us that our x value for the cheapest of the top 30% of printers is going to cost $233.35. Because again, remember these are x values, and the x values in this problem are dollars. Okay, so the last thing that we need to do some work with is standard normal curves. So we're going to talk about Z-scores, and then we're also going to use them in a real-world situation as well. So first, if we have a standard normal curve, what I mean by that is we have a normal distribution just like we've had, but the x-axis is going to be standardized. It's going to remain the same no matter what data set or what problem I'm looking at. The mean is always going to be 0, and the standard deviation is always going to be 1. So on this normal distribution that I've given you, as we said, the mean is going to be 0, and then I'm always going to use counting by 1 to get the rest of the x-axis with that standard deviation. So some things to notice is that When we're looking at a z-score, that is just the standardized labels of the x-axis. These numbers down here, we're calling the z-scores. They happen on standard normal curves. You'll notice that these are always going to be the same labels, and if the value that we're looking at is above the mean, so we're talking about over here, above whatever the average is, then all of these z-score numbers, it's always going to be a positive number. And if it's below the mean, down to the left, it's always going to be a negative number. Okay, so here's where z-scores are going to help us. We have a formula, it's going to be provided to you on the SOL test, that will calculate a z-score for us. We're going to input our x value, our mean, and our standard deviation, and it will tell us a z-score. So we can take any problem we're given and calculate a z-score so that we can compare data that might not necessarily be exactly the same. So let's just do some practice with some z-scores, and then we'll look at one of those situations where we're asked to compare stuff that we otherwise couldn't easily compare. Okay, so we're given a normal distribution with a mean of 60 and a standard deviation of 5. So normally what that would mean is our mean is 60, and then we're going to count by 5s to get the rest of the x-axis. Remember though that with a standard normal distribution, we're going to take whatever those values are and we're going to put them on the standardized curve, where the x-axis, or the z-scores, are always those same numbers. Okay, so let's look at some questions. What number is one standard deviation above the mean? So above our mean, if we go one standard deviation above, that means x is equal to 65. What number is one standard deviation below the mean? If we go to the left, that means x is equal to 55. And if we look at what number is 2 standard deviations above the mean, that's x is equal to 70. Now, if we're looking at z-scores for these, then from our mean, if we go 1 standard deviation, that means that the z-score where x is 65 is going to be 1 because it's 1 standard deviation. The 55, the z-score is going to be -1. And 70, that's 2 above, the z-score is going to be 2. So we're going to have 2 different ways that we can write the x value, and if we are using different situations, but z-scores will have all z's instead of having 2 variables, which is what's going to make it much easier for us. Okay, so let's use the formula a little bit. What is the z-score? So we're trying to find what z is equal to of the number 75 in this normal distribution. So remember, the formula that I just gave you for z-scores is x minus the mean divided by the standard deviation. So in this one, x is 75, the mean we were told was 60, and the standard deviation was 5. So if we just do some basic algebra 1 and simplify this, we'll know the z-score. 75 minus 60 is 15, and 5 stays in the bottom, so 15 divided by 5, we have a z-score of 3. That puts it way up here. What number has a z-score of z is equal to 2.2 in this normal distribution? So this time, I'm told what z is equal to. I'm asked what number. I don't know what x is. So I'm going to plug in the information that I have. I still know the mean, and I still know the standard deviation. And I'm going to use Algebra 1 to solve this. So I'm going to multiply both sides by 5 first. That's going to give me 11 is equal to x minus 60. Then I'm going to add 60 to both sides. And I know that x is equal to 71. So I was able to find that x value that corresponds with a z-score of 2.2. What number has a z-score of z is equal to -1.6 in this normal distribution? That, again, I'm being asked which number and told the z-score, so I'm going to plug what I know into the formula. I don't know the number, so I don't know x. I'm going to then simplify. So I'm multiplying by 5 on both sides. That gives me -8. And then I am adding 60 to get, oops, to get 52. Let's write this up here so I don't get stuck in those features. Okay. One last one. What is the z-score of the number 67 in the normal distribution? So I'm being asked what the z-score is. I know that the x value is 67. I know my mean, and I know my standard deviation. That's going to be 7 over 5. 7 over 5, we're always going to write z-scores as decimals, is going to be 1.4. That means that a score of 67 would be in the 1.4, so somewhere in this ish range on our standardized normal curve. Okay, so let's look at why we might want to do all of this silliness with calculating z-scores with the super easy formula. Okay, so let's pretend we're looking at test scores. And the class average on a math test was 84.5%. And the standard deviation was 4.4. Let's just first find the z-score for a test score of 94 so that we can standardize things. We know the mean is 84.5. We know the standard deviation is 4.4. And we know the score that we're wondering about is a 94. So to find the z-score, we're doing 94 minus 84.5, all divided by 4.4. That's going to be 9.5 divided by 4.4. If we plug that into a calculator, we get a z-score of 2.16. So that means then, if we think about our normal distribution from 0, that's a pretty good score because it's more than 2 standard deviations. That's way up there. That's a nice score. All right, so let's build on that a little bit. A national achievement test is administered annually to 9th graders. The test has a mean score of 100 and a standard deviation of 15. If John's z-score is 1.20, what was his score on the test? So we know that his z-score is 1.2. We don't know what his actual score was, but we can subtract the mean and divide by the standard deviation to figure that out. So I'm going to do 1.2 times 15 first. That's 18. And then I'm going to add 100. So we know that his score on that national achievement test was a 118, whatever that means. Okay, so here's the big kahuna. Here's why it matters. Let's say we have students taking different types of standardized tests. So Jill scores a 680 on the math part of the SAT. The distribution of SAT scores in reference to population is normally distributed with a mean of 500 and a standard deviation of 100. So we have a lot of information about Jill's score on that SAT curve. Kelly takes the ACT mathematics test and scores a 27. ACT scores are normally distributed with a mean of 18 and a standard deviation of 6. So notice here that I have two completely different x-axes. If I'm looking at Jill down here, Jill has a score of a 680, but the mean was 500. With that standard deviation, so she's up here somewhere. This is Jill. That's great. She did better than the average. If we look at Kelly, on hers, our mean was only 18. That's a really different number than 500. And we can do that standard deviation, but we can't just compare these two curves because the x-axis is completely different. And this is where z-scores come in. So we're going to standardize the scores, meaning we're going to find a z-score for each person, and then we can compare who has a better z-score because z-scores are all on that same x-axis. So let's do the z-score. I'm going to abbreviate for Jill first. Jill had a 680. We're going to subtract the 500, the mean, and divide by the standard deviation of 100. So that's going to give us 180 over 100, which is 1.8. So Jill's z-score is a 1.8. Now let's find the z-score for Kelly. Let's see, Kelly got a 27, We're going to subtract 18 and then divide by 6 there. 27 minus 18 gives us 9, and 9 divided by 6, that's going to be 1.5. All right, so now we know Kelly's z-score and Jill's z-score. So we can think about those on the same curve because we have the same x-axis of 0. So there's a 1, there's a 2. I'm not going to label the rest because both of our girls fit within that. A 1.8 is going to be up here somewhere, and that's Jill. A 1.5 is going to be a bit lower than that here, and that's going to be Kelly. So if we look at the standard curve, we know that Jill performed better because 1.8 is greater than 1.5, and Jill's score was greater than Kelly's score. So we can take data sets that aren't the same and convert them into a standardized format. So in this video, you learned how to, or you reviewed how to label a normally distributed curve, even on standard curves. We looked at calculating percentages and probabilities when it's not covered by the empirical rule. We also looked at figuring out x values when we're given the area under a curve. And then we looked at z-scores so that we could standardize data and compare and analyze. Go ahead and try the Now You Try problems.